In this section, I will show you how to describe different flop using Verilog. Okay, please see the code here. So these are, you must be familiar with this point, and this point, and this point. So the only thing you don't know maybe this positive, okay, negative. So this is the sensitive list, also the sensitive list. That is the signal or the event that will trigger the execution of this always block. So the meaning of the two lines is when positive clock occurs, then assign the value of D to the value of Q0, and the positive clock assign the value D to signal Q0. So this is exactly the function of a D-type flip-flop. Yes, positive clock assign the value here to here. Okay, let's see these statements. It defines a DFF with synchronous reset. Synchronous reset. So it also trigger this block at the positive of clock, and then first check the value of the reset. If reset is low, then the Q1 is resetted to the value of 0, or it will be assigned to the value of D. Yes, of D. So this is equal to a marks before the D pin of the D flip-flop. Yes. If this signal is 0, so this signal will pass through the marks and captured to Q1 at the right edge of clock. Or if this signal is 1, the value of this path will be marked to here and registered at the Q1 output. So this is exactly the function of a synchronous reset DFF, or you can say a DFF with synchronous reset. Okay, let's say this nice. At this sensitive list, it has two trigger events. One event is the positive of clock, and the other is negative of reset. So either of the two events will trigger the execution of these statements. Yes. So if the trigger is the negative of reset, this statement must be true. Yeah. This condition must be true. So Q output is assigned to 0. If it's triggered by the positive clock, it also first check the value of the reset. If reset is 0, the Q output is kept at 0 value. If reset is high, the value on D pin is assigned to Q2. So this is exactly the function of a synchronous. Yeah. A synchronous DFF. Sorry. This is exactly the function of a synchronous reset DFF. Also, if you already have the code, okay, if you already have the code, you may want to write some test bench to test it. Oh, sorry, one more thing. One point here. This assignment. Okay, this I think you may haven't seen this assignment before. This is not later than or equal operation here. This is non-blocking assignment. So actually, in procedural block, we have two types of assignment: non-blocking assignment and blocking assignment. Sorry, this is okay. Okay, if you use this symbol in a procedural block, this is called a blocking assignment. Okay, you just remember its name is okay. It's called a blocking assignment. If you use this symbol in a procedural block, it's called a non-blocking assignment. And the delay 1 unit here is used to emulate the CK to Q delay. You can delete it. This is all okay. Okay, I think I have explained all the new syntax here. So let's return back to the test bench. For these parts, you must be familiar now. This is something new to you, maybe. These are used to generate a periodic signal. The mean is always wait 5 simulation unit, wait 5 time unit, then execute the statement in this block. That is, for every 5 time unit, you will execute the inverter function of clock. That is, so this will generate a clock with period of 10 time unit, and we have defined the time unit as 1 nanosecond. So the clock period will be 10 nanosecond. Yes. So you can treat it also as an event trigger. Every 5 sim unit, every 5 time unit trigger this always block. So this is the method we use to generate the clock signal. Also, if there is only one statement inside a block, you can omit the begin end. You can omit the begin end keywords and just write it like that. So you will assign value to clock. Reset D, yes. Clock reset D. Okay. For reset, for clock, you just give the initial value. Okay, you just give the initial value here, and it will change. And the value of clock will change every 5 nanoseconds. Then you instance your DUT and collect the signals. Okay, let's try it using Verilator. Okay, let's make it. Okay, it informs us the signal has ended, and this is because it executes the finish statement and certain line and certain line of this file. Okay, you can see this is the waveform. This is because we have this statement here. Okay, it will save waveform for us, and the signal or the signal under this hierarchy will be saved. Okay, let's use GTK wave to save the signals. And I have received some waveform format files, so we can just load it. Okay, load it. Okay, let's check the function one by one. For the first register without reset, it always lets the data on D to Q0 and to the right edge of clock. So you can see D to Q. Okay. At this point, let D to Q. At this point, although this value on D has changed, but it will not change at Q output. Okay, the Q output is still keep and waiting for the next waiting for the next edge of clock. The Q output is changed. Okay. And let's check the waveform for the second register. That is a register with synchronous reset. So you can see at this point, the reset is inactive. So latch data. At this point, the reset is active, so the output will be forced to 0, no matter what the value on D pin is. At this point, the reset is released inactive, so the value on D will be latched on Q. Well, in my code, there is 1 nanosecond delay, or you can say one time unit, and the time unit is in 1 nanosecond. So there is 1 nanosecond delay after clock edge. So you can say this signal 1 nanosecond delay. Yeah. Yes, 1 nanosecond. Can we add a cursor here? Okay, I don't know. Can we add? Okay. You will find how to use GTK wave by yourself. Let's check the function of the last register. That is a register with a synchronous reset. You can see here. At right edge, the reset is inactive, so the Q output is the value of the input, and at this point, the reset is active, there is a negation of reset, so that this block will be triggered. Yeah, and after 1 nanosecond, the Q output is assigned to 0. And at this point, this block will also be triggered, but the reset is still 0, so the output is 0. At this point, reset released, so the D will be latched to Q. At this point, reset is valid again, so the Q is reset to 0. So you can say what is asynchronous? That is, the reset of Q has no relationship with the rising edge of clock. Yes, it's just related to the falling edge of reset. So that is, the Q output is asynchronous with the rising edge of clock. But for synchronous reset, the reset always happens at the rising edge of clock. Okay, this is the actual code, and this is the circuit schematic, or you can say circuit block diagram, and this is the waveform. So there is a requirement for you when you're learning the Verilog language. You have to consistency between the actual code, the block diagram, and the waveform. That is, give either of the three, you can figure out the other two. For example, if I give you the Verilog code, you can think about the block diagram and the waveform. If I give you the block diagram, you can code it using Verilog code or draw the waveform. Yeah, this is consistency between the three. This is a basic requirement for you to understanding how Verilog and hardware is works. Okay, can you remember why we define the signal as variable type? Can we define it as output wire and use them in the always block? Is this legal? Okay. As I have mentioned before, there is 2 assignments in Verilog for procedural blocks: the blocking assignment and the non-blocking assignment. So you must have confused which assignment can I use. So there is some guidelines, or you can say coding rules you have to follow. Coding rules. First, if you want to define sequential logic, so you must use non-blocking assignment. If you want to define pure combination logic, you choose blocking assignment. So the 2 coding rules are for code that will be synthesized. That is coding guide for DUT. For test bench, okay. For test bench, we don't tell sequential circuit or combination logic circuit. So use both is okay. But if you write something like sequential circuit, such as you use edge triggered always block, prefer the non-blocking assignment. For other place, prefer blocking assignment. So you just remember the 2. Okay. Don't confuse it. Remember the 2. For Y, I will explain it in later sections of this chapter. If you don't follow these coding rules, you could may confuse the simulation tool and may cause some problem. I will explain it later, in later section. Okay, this is the usage rule for non-blocking assignment and blocking assignment. For continuous assignment, that is code begin with that is code begin with assign. Okay, there is just only assignment operator using equal operator. Okay. So at this point, you have to try to understand how Verilog code works. That means how it works at simulation. We have explained Verilog is an event-triggered language. That is all the statements. That is the statements you write in continuous assignment and in initial always procedure blocks will be triggered only when the input signal is triggered. Or you can say there is an event at the input signal. Or the trigger hit and the sensitive list for always block. Yes. So that is, you have a positive clock, a negative reset event. Then this block will be triggered and this block will be executed. And for this, as there is no negative or positive precede the signal name, so this is level sensitive. Either 0 to 1 change or 1 to 0 signal change will trigger the entire procedure block. Okay. So this is called event trigger language. And the other character of Verilog language is parallel language. That is, if triggered at the same simulation time, all the triggered statements or procedure blocks will execute at the same simulation time. Yes, you may have noticed that for the combination logic design, when A or B is changed, all these statements will be triggered at the same time and execute. That is, evaluate the output value of all these statements. Yes. At simulation time, you can see all the value of this statement will be changed at the same simulation time. And for the different flip case, at positive clock, for example, this point. Okay, all the value on the D input will be latched on the Q output of the 3 registers. Yeah, so you can say Verilog is a parallel language. All these statements that has been triggered will be executed at the same time, if they are triggered at the same time. So there is a question for you: why Verilog behave like that? Okay, as you all know, the C or Java language, they are executed one by one, line by line. Okay. For a CPU time, just one instruction is executed. But for Verilog, it's parallel language and invent triggered language. Why? Sorry, I have given the reason for me. Okay, this is used to perfect match the behavior of a real digital circuit. So you can see just record a circuit we try to describe. For this example, if there is a rising edge and clock, in the real circuit, all the three registers will toggle. That is, will let data on D to Q. Yes. So that is because for a real circuit, this real circuit is parallel. So if you want to emulate the function of real circuit, the language you use should be parallel language. Yeah, the two can match. And why is event triggered language? This is also easy to perfect match the behavior of circuit. For example, if there is low clock event here, that is clock is keeps at low, or it keeps at high. Okay, so this DFF will not toggle. That is, the Q output will keep stable. So there is no need for you to execute this statement. Yeah, just keep the last value. Don't change the value. So this is why the language is event triggered. This is because the circuit itself is event triggered. Yeah, and for the compilation logic, if this input is stable, the output must be stable. There is no need for you to evaluate the value of output again. Okay. So try to understand the two most important characters of Verilog language and different it from other programming language you have learned. Okay, that's all for this section. In this section, you have the ability to use Verilog language to describe sequential circuit. That is just a simple register, a D flip-flop, and the D flip-flop can with synchronous reset or asynchronous reset. And you can try. Can you describe the function of a counter? For example, a 4-bit counter that can count from 0 to 15, then return back and continuous counting. Okay, this is a 4-bit counter. Can you describe this function using Verilog language? Okay, that's all.